So here's question number 6. This is from the 2013 BC exam. And typically question 6 is going to deal with series, and this question is no different. They tell us that a function f has all derivatives at x equals 0, and then they define the nth degree Taylor polynomial for f about 0 as p sub n of x. In part A, they tell us what f of 0 is. They tell us that the first degree Taylor polynomial with the x value of 1/2 tossed into it gives us an answer of -3, and they want us to prove that f prime of 0 is going to have to be 2. So this is the general definition of a Taylor series. A Taylor series representation for f of x is going to be, whoops, and this is not starting at the right value. A Taylor series representation for f is going to be found by developing this sum. So you need the function evaluated at 0 over 0 factorial times x to the 0. So that's what you see right here when I apply the index value of 0. And then when I apply the index value of 1, I get the first derivative evaluated at 0 over 1 factorial times x to the first. If I wanted another term, I would obviously apply the index value of 2 and then so on. But if we're going for a first degree Taylor polynomial, which they're telling us to work with here, p sub 1, what we're going to do is we're just going to stop at those two pieces, because what we have right here is we have an x to the first. This is a first degree polynomial. So 0 factorial is 1, x to the 0 is 1. They tell us what f of 0 is. F of 0 is -4. So I put -4 in place of this term. 1 factorial is 1. F prime of 0, I don't know. I'm trying to show that that's equal to 2. And then x to the first is just x. So here is my first degree Taylor polynomial as complete as we can currently get it. Well, what we know is we know that when we put 1/2 into this first degree Taylor polynomial, we get an answer of -3. So I put my answer of -3 here. I put 1/2 in place of the only x in this Taylor polynomial, and then it was a matter of solving that for f prime of 0. And if you add the 4 and then multiply by 2, you do show that f prime of 0 has to equal 2. In part B, it's pretty similar. We're dealing with a third degree Taylor polynomial though. So using the same definition that I wrote out on the previous screen, you can go ahead and tack 2 more terms onto that first degree Taylor polynomial, right? The second derivative evaluated at 0 over 2 factorial times x to the second, and then applying the index value of 3 gives us this piece. They tell us what the second derivative evaluated at 0 is, -2/3. They tell us what the third derivative evaluated at 0 is, +1/3. So I'm just putting -2/3 into this numerator. I'm putting 1/3 into this numerator. So 2 factorial is 2, 3 factorial is 6, and then as I went from this line to this line, it was just a matter of simplifying each of these individual terms. These two pieces I haven't really said anything about. Those are the two pieces that we had at the conclusion of part A. So these two pieces don't change as we go from part A to part B. These two pieces we need to develop, and in simplified form you'd be looking at what's on this bottom line. And then the last part of this, part C, gives us this new function h, and they tell us that the first derivative of h is going to be f of 2x, and we're also given h of 0 equals 7. We want to find the third degree Taylor polynomial for h about 0. So I didn't want to use the same notation here with the p and then the subscript. That was to represent the Taylor polynomial for f. So I'm just going to represent my Taylor polynomial for lowercase function h as capital H sub 3 of x. This would be my third degree Taylor polynomial for function h. So I'm applying the definition of a Taylor series expansion to the function h. So this is really the exact same thing that we had in part B, except we see the function h and its derivatives evaluated at 0 in the numerator rather than f. They tell us what h of 0 is, so h of 0 is what's going to go here, 7. They tell us what h prime of x is, f of 2x. Well, we need h prime of 0 to go right here. So what's f of 2 times 0? Well, that's just going to be f of 0. From part A, that was -4. So that's what's going to go in this numerator here. we need to know what goes in this numerator, and we need to know what goes in this numerator. So the second derivative of h would be found by taking the derivative of this equation. And when we do the derivative of f of 2x, we have an outer function f, inner function 2x. So a chain rule, derivative of the outer function gives us an f prime, inner function stays inside of that, and then times the derivative of the inner function. You want to evaluate this at 0. So when you evaluate this derivative at 0, you get f prime of 0 times 2. Well, from part A, we proved that f prime of 0 was 2. 2 times 2 gives us 4, so that's what we're going to put in place of h double prime of 0. And then the last thing we need is h triple prime of 0. So I need a derivative of this to develop h triple prime. So when I look at this piece of my second derivative, I see another outer function f prime, inner function 2x. So the derivative of the outer function is going to be f double prime, leave the inner function inside, and then multiply by the derivative of the inner function. So derivative of the inner function is 2. You see an additional 2 here, and that was because I just copied this constant 2 into my derivative. So when you simplify that and put 0 in place of the x to find h triple prime of 0, you get f double prime of 0 times 4. They gave us this value, f double prime of 0 in part B. It was negative 2/3. Multiply that by 4, you get negative 8/3. Take these results, 7, negative 4, 4, and negative 8/3, put them into the Taylor series expansion for h carried out to the third degree term. Simplify each individual piece, and you're looking at this for the third degree Taylor polynomial for h at 0.